SN2 reactions even more. So now we're going to talk about nucleophilic strength. That is the attacker. Let's talk about the attacker and how strong the effect is of that, right? Where am I here? Let's come here. And what is going on here? Just a second. There you go. So we're going to talk about the attacker, right? There's the nucleophile. How strong is the nucleophile? And we're going to talk about the solvent at the end of this conversation. So first of all, in order to have a concerted mechanism, we do need a strong attacker, right? So there's the attack. This should be coming here. This one is not such a good attacker. Water is actually pretty stable on its own, and doesn't have a negative charge there. So it's not really looking for reaction as much, and so consequently it is a weak nucleophile. So for SN2 to be favored, we need a strong nucleophile, and hydroxide is a good example of a strong nucleophile. I'll give you a couple more examples in a little bit. So this is going to be a fast reaction because this is a strong nucleophile. Now, some other strong nucleophiles are iodide, bromide, chloride, right? Thiol, and here's a sulfide, here's a hydroxide, here's an alkoxide, and here's cyanide, okay? So these should be memorized. Memorize all of these, 8 strong nucleophiles. And here's a couple other nucleophiles. They're weak, although we will see that they will act as nucleophiles some. But these are the ones that we have the eye out for when we're dealing with SN2 reactions, okay? So you should be able to determine if a nucleophile is strong or weak. And if you memorize these, it's going to help you do that. You're going to have to memorize these. So in general, anions, right, are strong nucleophiles. Notice these all have a negative charge. And they also have lone pair of electrons, of course, I guess, right? So they're anions, and polarizable make them better. And polarizable, by that, what we mean is if they're big, okay? If they're really big, that means that they're really polarizable. So you can imagine that if you've got a negative charge on an iodide, right, and you've got a negative charge on a fluoride, right, this negative charge has got acres and acres of surface area to get lost on, right? But over here, it's much smaller. So this is polarizable, which makes, there's no E in that, which makes this a better nucleophile, okay? So if it has a charge and if it's polarizable, then it is a good nucleophile. Now let's talk about how solvent affects nucleophilicity. So we have protic solvents and polar aprotic solvents. A protic solvent is something that has got an ionizable hydrogen on it, right? Right? Look at all those hydrogens that are bonded to an electronegative element. Protic, you know what that means? They're capable of hydrogen bonding. That's really what protic means. There's an electronegative element here, which I oftentimes signify as Z, right? You see ZH, right? ZH, FO or N, bonded to a hydrogen is going to make a solvent which is capable of hydrogen bonding. These have hydrogens on them, look at that, but it's not on an electronegative element. That's on a carbon, right? Here's a, oh, there's no hydrogens here. It's just, methyl groups, right? And there's some hydrogens here, but it's not an electronegative element. And there's some hydrogens here. These are methyl groups, but they're not an electronegative element. So it's no H bonding over here. No hydrogen bonding capable. On polar aprotic solvents, aprotic means it doesn't have the proton on an ionizable hydrogen. So then here's the reason why. Protic solvents make hydrogen bonding, and they stabilize the anionic species very well, like too well, okay? Aprotic solvents stabilize both the cations and the anions. Let's look at the reaction diagram for this. So, and this is super interesting. What is the activation energy here for the blue reaction? Right? There's the activation energy. Right? Where's the activation energy for the red? Right? There's another activation energy, right? So, and here's the reason why. With polar aprotic solvents, the nucleophile, look at there's the nucleophile, is not hydrogen bonded to anything or doesn't have the capability of really strong dipole interactions. So since it's aprotic, Since this DMSO, here's an example of DMSO, is aprotic, it doesn't stabilize the anions very well, and therefore, since it doesn't stabilize the anions very well, the potential energy of the reactants are higher, which makes a lower activation energy, right? You see that? Because it brings the energy of this. In other words, they're already sort of unstable, and they're ready to just fall over that hump. Okay, so the lower activation energy makes that reaction much faster, and so in order to have good SN2 reactions, we need a strong nucleophile, which means charge, right, is an anion, and it's large, right, for charge and large. That wasn't meant to be, it wasn't meant to rhyme, but it needs to be polarizable, and it needs to have a charge on it, okay? Strong nucleophile, and it needs to have a good solvent, which in this case is polar aprotic, so that it doesn't stabilize the nucleophile, right? We don't want that guy stable. We want him reactive. All right, hope that's helpful. Go practice.